Good morning, students. Let us start the class on information theory. In the last class, I have been discussing about this particular exercise. Construct a model for the collection of 400 cars whose information is to be transmitted every second. The test data given is as follows. On an average, 200 cars were heading straight, 100 turning left and 100 turning right. In the subsequent time period, out of 200 cars heading straight, 100 of them reported going straight, while 50 of them turned left and 50 of them turned right. And out of 100 cars that reported turning, 50 of them continued their turn during the next period and 50 of them remained heading straight. Now, the dynamics of the cars did not allow them to change their heading from left to right or right to left during the subsequent periods. Means there is no left to right transition. There is only left to straight or right to straight transition, and there is no right to left transition. Calculate the source entropy and the average information rate. The model is given, we have to find out the source entropy and the average information rate. Let us proceed with the exercise. Now we require three states. One is left, straight and right, and we have the data for all these three. The state probabilities are given as capital P1 is 100 by 400, that is 1 by 4. This is given now. And P2 is given as 200 by 400, that is 1 by 2. And P3 is given as 100 by 400, that is 1 by 4. In the earlier cases, we had assumed each state has been equal probability. But in this case, specifically it is given about the probability of left, probability of straight and probability of right in the beginning itself. So that is the state probability. Now, as the residual influence lasts for one reporting interval, means from state to the next state, this transition is happening. So the transition probabilities can be calculated with the present and previous headings as, you can show this, P of straight and straight is 100 over 200, that is half. P of right to straight and left to straight is 50 over 200, that is 1 by 4. And straight to left, straight to right is 50 over 100, that is 1 by 2. P of left remaining left and right remaining right is 50 out of 100, that is 1 by 2. And there is no probability of moving from left to right or from right to left. So the probability is basically 0 for such cases. So all these transition probabilities are given in the exercise. So now the state diagram can be written as shown. This is the state diagram now. State 1, state 2 and state 3, left is probability having half. Then from state 1 to state 2 it can go, that means left to straight, and again in state 2 again it can continue straight, and in state 3 from state 2 to state 3 it can move right, again in state 3 it can continue right, or it can again come back to straight, again from state 2 it can come back to state 1 by means of left turn. And all these are already given now. P1 we have computed 1 by 4, P2 as 1 by 2, P3 as 1 by 4, and all the transition probabilities are also given. You can see that between 1 to 3 or 3 to 1 there is no transition there, which means left to right or right to left transition is not there. This is typically a situation in a highway. So the entropy of each state is computed based on the symbols emitted as H1, H2, H3. H1 is half Lg of 2 plus half Lg of 2 is half plus half is 1 bit per symbol. H2 is half Lg of 2 plus 1/4 Lg of 4 plus 1/4 Lg of 4 equals half plus half is 1.5 bits per symbol. And H3 is half Lg of 2 plus half Lg of 2 is half plus half is 1 bit per symbol. These H1, H2, H3 are computed based on these states. Hence, the source entropy is given by capital H is P1H1 plus P2H2 plus P3H3. That is 1/4 into 1 plus half into 1.5 plus 1/4 into 1 is 1.25 bits per symbol. Therefore, the information rate R is small rs into h. That small rs is 1 and capital H is 1.25 bits per symbol. So it is totally 1.25 bits per second per car. You get this point? We are modeling the car's movements and we are finding out what may be the number of bits required for this transmission of information. So we have finally got it as capital R equals 1.25 bits per second. This is per car. Let me proceed to the next exercise, that is exercise 16. For the example stated in the beginning for the Markov source emitting the symbols A, B and C. Please recall that exercise which I had solved earlier. Find the source entropy as well as the entropy of the first and the second order. At that time we did not find out the first and the second order source entropy. That means emission of single symbol, emission of two symbols and verify that G1 is greater than or equal to G2, that is greater than or equal to H. What does this mean? We already had a small theorem where we had shown that when the symbols are statistically dependent and when the sequence length is large, actually the information content per symbol will be reduced. That means we can really conserve the bandwidth. That means whenever an information source is having a statistically dependent symbols, it is always a good idea to send a larger message or a larger sequence such that the net information content per symbol is going to get reduced. That is the idea there. Again, to give you an example of this packet switching, let us say in a packet we are packing 100 bits and all these 100 bits are statistically dependent. Now it is advisable to have a packet with the 200 bits such that the average information content per symbol is going to be reduced there, but we are conveying more and transmitting less. So if a packet is containing 200 bits, that is more efficient than two packets containing 100 bits. That is the idea. Instead of sending a packet containing 100 bits, we are sending a packet containing 200 bits single packet instead of two packets. That means naturally there is a conservation of the resource. But the disadvantage there is the packet should be much larger. That is the problem there. So based on this, we always come to a conclusion that when the statistically dependent symbols are present in an information source, it is better to send sequences which are larger so that our information rate can be reduced. That is the idea. So in this exercise, he is asking us to prove that G1 is greater than or equal to G2 and G2 is greater than or equal to H. H is the source entropy as such. Now let us try to solve this problem. The entropy of each state is H1 is half Lg of 2 plus 1/4 Lg of 4 plus 1/4 Lg of 4, 1.5 bits per symbol. Similarly, H2 and H3 are also 1.5 bits per symbol for that particular Markov source which we had discussed as emitting symbols A, B and C. Now, capital H is P1H1 plus P2H2 plus P3H3 equals 1 by 3 into 1.5 plus 1 by 3 into 1.5 plus 1 by 3 into 1.5. There we had assumed all the states having equal probability. So the capital H is 1.5 bits per symbol. Now, first thing is we have to compute G1, then we have to compute G2. Let us compute G1. We had already seen the tree diagram earlier. Now, from the tree diagram, P of A is 1 by 3 into half plus 1 by 3 into 1 by 4 plus 1 by 3 into 1 by 4, that is 1 by 3. Similarly, P of B and P of C is also 1 by 3. So we can find out G1 now is 1 over n into summation of all those individual probabilities of single symbols that is 1.585 bits per symbol. Now let us compute G2, that is having two symbols. Now from the earlier calculations, again from the same tree diagram, we can find out P of AA equals P of BB equals P of CC is 1 by 6. Similarly, P of AB equals P of AC equals P of BA equals P of BC equals P of CA equals P of CB equals 1 over 12. Now, G2 is 1 over n, here n is 2 and 3 into 1 over 6 Lg of 6 plus 6 into 1 over 12 Lg of 12. We get G2 as half into 1.293 plus 1.793, that is 1.543 bits per symbol. So, now G1 is greater than or equal to G2, that is satisfied. G2 is greater than or equal to H, that is satisfied. How? H here is 1.5 and G1 here is 1.585 and G2 here is 1.543, which simply proves that when there are more number of symbols, the information content per symbol gets reduced because the symbols are statistically dependent. Then it is advisable that we can have sequences of larger length, albeit we have to handle the overhead of managing the sequences having a larger length. Okay. Just to give one more example for the same situation, let us say a family is containing 50 members. Let us say it's a joint family containing 50 members. Now, complete family wants to go for a trip. Now, they have two choices. They will have to go by car, or they will have to go by tempo traveler, or they will have to go by a big bus. If they go for a big bus, all the 50 people can travel in the single vehicle. There they have a distinct advantage. But the problem is that bus is much bigger. So that has to be taken care. Otherwise, they can go for, let us say, 2 tempo travelers. Each tempo traveler, let us say it is containing around 25 people. So 2 tempo travelers. But here the problem is, because there are 2 tempo travelers, there is a need of synchronizing both the tempo travelers. Wherever they stop for breakfast or lunch or dinner, they will have to be in sync with each other. This problem will not occur if they travel in a single bus. Now, instead of the tempo traveler, if they decide to go by individual car, then each car can hold 5 people. They need 10 cars now for 50 people to go. It will be very difficult to synchronize all the 10 cars and to keep count of the 10 cars wherever they go. That is a much bigger task of managing the 10 cars communication. So, which means what? If at all they go by car, then the information content per symbol is much larger because they have to handle other things also. If they go by tempo traveler, then the information content per symbol is slightly lesser. If they go by a single bus, then the information content per symbol is still lesser. So, whatever example I gave you now, that we can relate it to G1, G2, G3. Where bus can be related to G3, tempo traveler can be related to G2 and car can be related to G1. The least one is always the source entropy that way. So that is how it is always advisable that in the communication systems, if we transmit large number of symbols which are statistically dependent, we are going to save the cost of the transmission. That is the idea of these exercises. Now from now on, there are some additional exercises. I will not be solving all these exercises in the class. I will ask you to go through the notes again and go through all these exercises on your own. Anyhow, I have solved all these exercises in the notes. But as the time is lesser, I will have to continue to the next topics as well. So, all these additional exercises, I will just skip it and I expect that you go through the notes and understand all the solutions. So let me proceed further. There are many exercises which I have already put in the notes. Please go through all of them. They are all similar in nature. Now let me come to the summary of this module. Summary. Information, it is the one which was so far being unknown and now being known. Self-information means the information that is independent of other messages. Mutual information means the information that is dependent on some other self-information. Okay. So that way, in the future modules, we are going to deal with the mutual information only to a larger extent, because we know that each information is dependent on the preceding information as such. So there is always a statistical dependency in real life. So I of m equals 0 when Pm equals 1 as the event is certain. This I had already discussed in the beginning. I of m will be greater than or equal to 0 when probability of the message is in between 0 and 1. Whereas information is not going to be, it is not equal to infinity when Pm is 0 as the event is observed. We need not say that when the probability is 0, the information is infinity. We cannot say that way. Just because it is logarithmic, we cannot say as the event is observed. Entropy is defined as the average information content per symbol, generally expressed as bits per symbol. And the rate of information is the average number of bits that are transmitted per second. And entropy of state is computed based on the symbols that are emitted. In the beginning, when the system is in a particular state, it is going to emit symbols, and that is utilized for computing the entropy of the state. Later on, when a transition is happening between state to state, transition probabilities come into picture. Probability of state is computed based on the symbols that are received. Probability of state is also called as stationary distribution. I did not get into all these statistical names till now, because it is really not so much necessary for the understanding of information theory. Still, as they are of mathematical importance or as they are of historical importance, I am listing them here. Probability of state is also called as stationary distribution, and we have already notified it as capital P1, P2, P3. Entropy of sequence is also called as entropy of the adjacent source. This is a typical word used in the textbooks. There is a sequence, and we simply call it as single symbol sequence, two symbol sequence, and three symbol sequence. But here sometimes they call it as G1 is one source, G2 is the adjacent source, G3 is the adjacent source, that way. So in such cases, textbooks sometimes refer to this as entropy of the adjacent source. You should simply understand that it is the entropy of the sequence itself. Who is unmuted, please remain muted. Lastly, I am summarizing all the formulae. G1 is 1 over 1 because n is 1 here. H of s bar, this is the notation in some of the textbooks. Now this is called as a second order system because H itself is the first order. So G1 is naturally the second order. Similarly, G2 is 1 by 2 H of s bar to the power of 2. Don't consider it as a square. It is not that, it is simply a symbolic notation. Now this is a third order system, and G3 is 1 by 3 H of s bar to the power of 3, that is a fourth order system. So in general, Gn equals 1 over n into H of s bar to the power of n. This is the general formula. So with this, I am ending the first module. I am going to start the second module now. Let me take a small break for sipping water. So students, just to have a brief recap of whatever we learnt in the first module. We learnt about the basics of information, basics of measurement of information, and the basics of dependency of information, and basics of transmission of information in terms of sequences. Okay. Now from now on, we will move on to the second module, where we are going to deal with the source coding as such. As you already know, in the information source we have predefined character set or predefined symbols. Now when the symbols are being emitted by an information source, we will have to represent the information in terms of binary digits or bits. So how that can be achieved is going to be studied in the second module, that is called source coding. Actually, as per your syllabus, the second module is the other one called channel capacity. But what we have decided is we will teach you source coding itself as the second module now, and later on we will move on to the third module, that is channel capacity. Later on we will move on to the channel coding. That is how we have a correct flow there. First let us discuss the information source, and then let us discuss how the information source can be characterized for source encoding. And later on let us see the characteristics of the channel and what are all the problems we face with the channel. And after that let us see how the channel coding can be performed in a communication system. And lastly, in the fourth and in the fifth module, let us see how the transmission errors can be detected and corrected in a mathematical fashion. So, even though in the syllabus chapter 2 or module 2 is the third one, in our coverage we will do the third one first and later on we go to the second one. Let me start with source coding. Source encoding is the process by which the output of an information source is converted into a binary sequence, as I have already told you. The source encoder assigns variable length binary code words to blocks of symbols in order to reduce the bit rate without reducing the information content. Let me again annotate. Please understand, the source encoder assigns variable length binary code words to blocks of symbols. Why? As I have been discussing earlier, when the symbols are statistically dependent, then whichever is occurring frequently can have lesser number of bits, and whichever is occurring rarely can be having a larger number of bits. Otherwise, if at all we have to have a fixed length of bits for all the characters, then we are unnecessarily wasting the resources. So the source encoder is going to assign variable length binary code words. Please understand this. To blocks of symbols. Blocks of symbols is nothing but a sequence. In order to reduce the bit rate, see, in order to reduce the bit rate without reducing the information content. The information content is not going to be reduced, okay, because we are relating information with probability, that is real. So bit rate will be reduced. When bit rate is reduced in the same channel, more number of communication purposes can be achieved. That is the idea. Anyhow, this is again a revision of whatever we had discussed in the beginning. Now, I have been telling about Claude Shannon. Let us see in the beginning how Shannon gave an idea of having this different types of variable length codes for the given set of sequences or symbols. Let us see that. So initially we are going to discuss the Shannon's encoding algorithm. This is one of the methods of assigning the code words for symbols. Let there be Q messages, M1, M2, M3 up to MQ. These are the messages. each containing capital N symbols. And let the probabilities of the messages be P1, P2 up to PQ. Why I am putting a capital P here? Because it is a message, it is not a symbol. It is a message. Just like in English word, we can call this all the masses words. Words contain alphabets. That is why a capital P is used here. As we already know that Gn tends to H as N tends to infinity, right? We already know. If the number of symbols in a sequence is going to tend to H as N is going to infinity or N is increasing, this we have already seen. So our goal here is to find the unique code word Ci for each message Mi with code length Ni bits. See, we have these many messages. Let us say M1, M2, M3 like that up to Q messages. For each message, we should assign a unique code word. That unique code word is Ci and it should have a code length Ni. Now the code length can vary from message to message because we are basically going for variable length messages. The messages which are more probable will have less number of bits. The messages which are less probable will have more number of bits. That is how we are going to conserve the number of bits per second or the information rate. So, our goal here is to find unique code word Ci for each message Mi with code length Ni bits such that the average number of bits per symbol Hn cap is as close to Gn as possible. Please understand this. We do not want to unnecessarily pack more information content and we do not want to increase the symbol rate or information rate. So, average number of bits per symbol, we use that as Hn cap. This should be as close to Gn as possible. These terminologies again we are going to use in our exercises. So right now you don't have to worry how do we arrive at this Hn cap. The calculations are really simpler, but there is a need for remembering the basics always. Okay. So average number of bits Hn cap is as close to Gn as possible. For achieving this objective, the algorithm given by Shannon is as follows. Shannon thought of an algorithm which is basically a simple algorithm. When we solve the problem, you will come to know it's actually a simple algorithm. There are still simpler algorithms later on. After Shannon gave an algorithm, later on one more scientist called Fano gave an algorithm, and we have one algorithm called a Shannon-Fano algorithm. Okay, so we are going to study all that in the next classes. So, let us see the steps which Shannon declared for achieving our goal now. So, the first step is let the messages M1, M2 up to MQ be arranged such that the probabilities are in the descending order or decreasing order. We already know that lesser probability means larger number of bits. So, let these messages be arranged such that the probabilities are in the decreasing order or the descending order, means P1 is greater than P2 greater than PQ. That way, let it be arranged. The next step is let Ni be an integer such that Lg of 1 over Pi is less than or equal to Ni, and that is less than 1 plus Lg of 1 over Pi. When we arrange these symbols in the order of the probability, let us have this Ni, which is nothing but the number of bits now, which we have to find out. Let this number be in between these two, Lg of 1 over Pi and 1 plus Lg of 1 over Pi. This Lg of 1 over Pi is always a decimal fraction. It's a fraction, sorry. Why should I say decimal fraction? It's a fraction. So, now the number of bits for a given message cannot be fraction. It has to be an integer. But when we compute this entropy, we get all fractional things. So, Shannon defined the number of bits in such a way that let ni be in between these two. Let it be greater than or equal to Lg of 1 over pi. If this is an integer, then ni can be equal to that. Otherwise, let ni be less than 1 plus Lg of 1 over pi. This is the second step in this algorithm. Now the third step, let there be a fraction called capital Fi. And that fraction is equal to summation of k equals 1 to I minus 1 of pk. Pk means corresponding to a particular probability. Obviously, f1 equals 0. Why? f1 equals 0. Why? We will see later on when we compute this value. Then the code word for the message mi is the binary expansion of the fraction fi up to ni bits. Code word for the message mi, any given message for which we can assign a code word which is a binary expansion of the fraction up to ni bits. You will have to revise your Boolean algebra. You will have to revise your digital knowledge now, because you have already studied how to convert decimal to binary, binary to decimal, all those things. Now you will have to revise how to convert binary fraction into decimal or decimal fraction into binary. In fact, there is a method called double method. Whenever an integer has to be converted, you continuously keep on dividing it by 2, and finally whenever you have a remainder, you add that. That is called double method. That is continuous division. That is for integers. But how do you convert fractions into binary? For converting fractions into binary, you should go for the other counterpart. Instead of continuous division, you should go for continuous multiplication. By means of continuous multiplication, that particular fraction has to be converted into binary. And when we arrive at that binary word, we decide about the length of the word as up to ni bits, because we have defined already what is ni, and we will choose that particular code word. That code word will be assigned for the given message. So the code word for the message mi is the binary expansion of the fraction fi up to ni bits. That is why a fraction is defined here. So ci is fi in binary totally ni bits. This is how Shannon's algorithm is defined. Let us see an example. Only when we see an example, it will be more clearer to you. So let us see one example now. Exercise 1. Construct binary code for the following source and find out the code efficiency and redundancy. Now this source is emitting these 5 messages: S1, S2, S3, S4, S5. Either you can call it as messages, either you can call it as symbols. It does not matter at this particular instant now, because if it is English alphabet, we can simply say it is 5 characters, whereas here the source is characterized by 5 distinct messages. Now the probabilities are given for each message. See, I am writing the capital P, not small p. Why? It is not a probability for a symbol. It is a probability for a given message, where source itself sends 5 messages. If at all I have to give you a real example, right now I am listening to a crow which is making a sound at the adjacent tree. Now can a crow be represented by this yes? Let us say the crow makes 5 distinct sounds. When it is normally simply cawing. Do we say cawing? I don't know. When it is normally simply making sound, that we can say it is around S1. That is the typical crow sound. If a crow is seeing a food, then it may make the sound that is S2. If the crow is seeing another crow, then it may make a sound this S3. And if a crow is feeling a danger, I am just giving some vivid examples. If it is seeing a danger or a threat, it may make one more sound, S4. Let us say a crow is seeing one eagle, then it may make one more sound, S5. I'm just giving some 5 different cases. So if the crow is able to make these 5 different sounds, now somebody made a study of the crow, imagine that way, that the probability of crow producing these 5 sounds is given this way. When you sum all of them, you will get 1. When you sum all of these, you will get 1. That means ultimately crow is going to make a sound, but the sound can be of 5 types. I'm just giving a very crude example just for you to understand this problem, that's all. Procedure is really very simple later on now. So, information source is given which is going to emit 5 messages. That's why I told you it need not be always characters, it need not be always alphabets. In case of a crow, it can be just 5 sounds also. I hope you got it now. That is why we are using this capital P, because it is not an individual symbol. It is now a message. Whenever a crow is making a sound, that is basically giving a message either to a nearest crow or to some other crow or to the people who are listening to the crow, like you and me. Only me, as far the timing is concerned, it is me who is listening to the crow. So let us see how to solve this problem. Actually, problem is simple. Answer is, as the first step, each message has to be arranged in the decreasing order of the probability. Then Ni has to be calculated for the particular Pi as follows. So let us see, this capital P is a set of all small p here now. Just like a capital S is a set of all small s here. So this is the tabular column, where you can see here now, serial number 1 till 5, we have arranged message in terms of the decreasing order of probability. You can see S2 is arranged first because its probability is highest 0.4. Then S1, then S5, then S4, then S3. That is 0.4, 0.25, 0.15, 0.12, 0.08. Now, we have to find out this number of bits Ni. Let me come back to this tabular column later on after showing you the procedure for each step. Otherwise, you will not understand this now. I will come back to this later on. Let me show you the solution. N1 is calculated as Lg of 1 over 0.4 should be less than or equal to N1 should be less than 1 plus Lg of 1 by 0.4. Which means Lg of 1 by 0.4 is 1.32. This is what Shannon proposed as the second step in this algorithm. Now 1.32 has to be less than or equal to N1. It has to be less than 1 plus 1.32. That means N1 has to be in between 1.32 and 2.32. Obviously, N1 is equal to 2. Why? N1 has to be an integer. Now the number of bits that represent the message, that particular message what? S2. The particular message S2, which will be represented only by 2 bits. Why? Because that is having the highest probability. Whichever is having the highest probability will have a lesser number of bits. Just go through this tabular column once again. 0.4 corresponds to 2, 0.25 corresponds to 2, 0.15 corresponds to 3, 0.12 corresponds to 4, 0.08 corresponds to 4. Now recall this. Let me annotate this. Now recall this. Larger the probability, lesser is the information content. Lesser the probability, larger is the information content. Now that is satisfied here. 0.4 is larger, represented by 2 bits. 0.08 is smaller, represented by 4 bits. So the logarithmic nature of the I of m, the self-information, is satisfied here. That is what we wanted, right, in the first place. So that is how we find out the number of bits for each message now. That is why Shannon proposed this particular way, where the number n has to be in between these two extremes. So when n1 is in between 1.32 and 1 plus 1.32, that is 2.32, naturally n1 has to be 2. Similarly, LG of 1 over 0.25 has to be less than or equal to n2 and it has to be less than 1 plus LG of 1 over 0.25. Now this has to be between 2 and 3. Now as n2 has to be integer, now we have got, in this particular case we have got at both the sides, we have got an integer itself. n2 has to be integer. That is why Shannon put one condition here as less than or equal to, because we want to conserve the number of bits. Obviously n2 need not be 3 bits, n2 can be only 2 bits. Okay, so n2 equals 2 in this case. Similarly, for the other one, LG of 1 over 0.15 less than or equal to n3 less than 1 plus LG of 1 over 0.5, n3 we get in between 2.74 and 3.74, n3 will be equivalent to 3. And similarly for the fourth one, n4 has to be in between these two extremes, we get n4 equals 4. And lastly, n5 has to be in between LG of 1 over 0.08 and 1 plus LG of 1 over 0.08, we get 3.64 and 4.64, n5 can be obviously 4. So based on these results, we have filled this second column now, 2, 2, 3, 4, 4. Now the third step is we have to find a fraction now. That fraction is going to be a summation now. Let us see how to find this fraction. And let me tell you why we got in the first place fraction as 0. Let us see that. So fraction is calculated as f1 equal summation of k equals to 1 to 0 of pk. See, k equals 1 to 0. Let me go back to that previous definition where fraction fi is summation of k equals 1 to I minus 1 of pk. So in the first place, it is simply the very first particular highest probability message. That means when that is being emitted, we don't have to consider the other ones. So naturally for the first case, f1 is summation of k equals 1 to 0 of pk, that is equal to 0. Now f2 is 0 plus 0.4. We have the next probability now, that is 0 plus 0.4, that is 0.4. f3 is 0.4 plus 0.25, that is 0.65. We have to keep on accumulating the previous result here now. f4 is 0.65 plus 0.15, that is 0.8. f5 is 0.8 plus 0.12, that is 0.92. Let me go back to the tabular column. Very first one is 0, then 0 plus 0.4 is 0.4, 0.4 plus 0.25 is 0.65, 0.65 plus 0.15 is 0.8, 0.8 plus 0.12 is 0.92. Now when you add 0.92 to 0.08, you will get 1. That is unity. That means out of all these 5 messages, it is the unity indicates that this is going to emit one of these 5 messages. Anyhow, the information source is going to emit one of these 5 messages. That is for sure. That is why when you add all of them, you will get unity itself. So as per the definition of the fraction, the very first one is 0. Add this with the first probability which is highest, 0.4. Then keep on adding 0.4 plus 0.25, 0.65. Then plus 0.15, 0.8, plus 0.12, 0.92. Obviously, you don't have to add the last one because 0.92 plus 0.0 you are going to get 1 itself. That is how this fraction is obtained. You can see this fraction is always between 0 and 1. 1 means certainty, 0 means absurdity. Now fraction is in between 0 and 1. Now we have to convert this fraction. This is a decimal fraction. We have to convert it into a binary fraction. So I have already done this binary. Anyhow, now it is time. In the afternoon's class, I will show you a slide where the exact procedure for decimal fraction to binary fraction is discussed. If at all you don't recall the basics, let me show you that in the afternoon's class. For the time being, just see this table itself. 0 is nothing but 0.00. Why? because we have already discussed that Ni has to be equal to 2 in that case. So we write it as 0.00, where the 00 itself is the code for the very first message. And next, when you convert this 0.4 into binary, you will get 0.01. Discard the integer part because it is anyhow fractional part. Take this fractional part, 01 itself is the code for 0.25. Next, when we convert 0.65 into a binary fraction 0.101, we can keep on continuing till any number of bits there, because sometimes the binary fractions will never end. But we don't have to go that way because we have only the